I think so.
Yeah.
Although I've lost my window in which I joined, so that would be good to find that. Shoot. Okay, I'm just going to exit all my windows and start over.
Perfect. Wonderful.
Okay, thank you. All right, we are at time, so let's begin. Welcome to the COSE Working Group session on Tuesday. I'm Mike Jones. My co-chair, Ivo, is also with us virtually. Hi, Ivo. So the note well, you should be familiar with. Um, all of you in the room, please join the light client on MeetEcho, which you can do from the agenda. That will record your attendance. Failing that, you can use the QR code, but we want you to use the client so that you can queue for being in the microphone line and other things. So there's the agenda, which I'm sure you found or you wouldn't be here. MeetEcho information. First, request of the room. I need one or more note takers to type into the collaborative meeting notes tool, the link of which is both in the agenda and on the screen. Michael Richardson, a man among men, a hero in the room.
Why are you so gender biased? I want to be something else among them.
A person among persona. Is anybody willing to tag team with Michael? Just make sure that you're fixing his mistakes, okay?
Oh.
Oh, that.
That needs two.
Anybody willing to follow along? Justin, can you correct Michael?
Sometimes, but I've got other stuff to do in the background here, so
Okay.
I can help a little.
Okay.
I see also Christian will be helping. He wrote on the chat.
Oh, thank you. And thank you, Eva, for monitoring the chat. That would be good. So, content from your chairs. We have two new RFCs, yay. The type header parameter is done, 9596. And the CWT claims and headers is done, 9597. Then we've also submitted the COSE key thumbprint for publication. Yay, Hannes breaks out into cheers. I believe the IANA status is approved. And so at this point, I believe we're waiting for AD follow-up by Paul. Is Paul in the room? Now, we are minus our AD right now, but there we go. So there's a couple drafts we haven't touched since Brisbane, and I just thought I'd call them out. We haven't touched the BLS key representations. Before Brisbane, we did update it to use the XY uncompressed key representation. And in fact, the Jose JSON Web Proofs work uses that key representation now. There hasn't been sufficient changes to BBS signatures to warrant touching that. I believe Mike Prorock will mention this, but we haven't updated the Falcon draft, in part because, well, I'll let Mike speak to that. We have a full agenda. You can look at the agenda online, but I'm going to stick to it for time because otherwise we won't get through it. We have a lot of good content. Oh, wrong button, not share screen. Let's share slides. With that, let's have Hannes come up for one of many times. Talk about HPKE.
Yep, giving a presentation on behalf of the authors listed here. Just a quick summary. Minor hiccup during the submission. I was in the wrong branch, submitted the wrong document. Apologies. But corrected that. Version 09 is fine. Going to speak about the changes we made from since the last IETF meeting from 7 to 9. Okay, next slide. So there are a couple of changes in the document. And I think most importantly, we changed the way we deal with the context information thanks to contributions from Lawrence. Previous versions of the document used as indicated above this, meanwhile famous COSE KDF context structure, which was an input to the HPKE, which was then led to the derivation of different keys. And that is a parameter in the HPKE info field of one of the APIs. I think the setup API. And now we switch to a different structure. Lawrence created a new one. It's called the recipient structure, which is, as the name indicates, it's used as part of the computation of the recipients field. And it then, as a consequence, takes the parameters of that structure and includes it in the authenticated data. So it's it works a little different. Instead of going into the key derivation, it goes into the authenticated data. However, I had reached out to Paul Van Oorschot, and he said both approaches are fine from a security point of view. Of course, assuming that you put the same information in there, but the structure allows you to do so. It just deals with it in a different way, and I have an example to illustrate what that means in the next slide, and so I get to that, explaining on like the difference in case you haven't followed the discussions on the mailing list. We also changed the terminology. Previously, we were talking about a single layer or a two-layer structure or multi-layer structure, and now we call it HPKE direct encryption mode for the case where we send the data to one recipient. So there's no recipient structure in the payload. So it's sort of kind of the optimized version. And then there's the other mode, which is this key encryption mode, which is sort of allows you to send an encrypted payload to multiple recipients. So those are the two modes. We had that for a long time. We just gave them different names. Now we changed the names, not in line with the Jose work. So there may be some further changes here, but it's probably something, if you look at the document editorially, that looks quite different. We also changed a couple of other parts in the document, smaller changes or like minor edits. The initial cipher suite list was reduced to only include those algorithms that we cared about most. So we axed probably half of them. Of course, there's always the possibility to register new algorithms later when the need arises, but we didn't want to stuff too much in there. We also shortened the labels. Like those are just the representations, so it has no meaning for the on the wire representation, but it's for readability. It's probably better. We also changed the name of the key to get it in line with what we have in the COSE work. It's probably for better readability if you happen to read both documents side by side. There was more text for the COSE key representation, so at some point in time we added ways to represent those HBKE related keys as a COSE key structure, and that there's more text now, and a bunch of other editorial improvements. So like if you look at the diff, looks like a lot of change, but so here's the thing. So the COSE recipient structure that Lawrence came up with is on your left-hand side, and you see it has it includes the protected header fields, which is the important part here. So it's a slightly different construction. So in the example on the right-hand side, what that would mean is in the protected header field of the recipient structure, which is the one in here, that has one protected header field here in this case, namely the algorithm. So the algorithm would be included in that recipient structure and thereby protected. So that would be the context that is bound to that HBKE invocation. So now what we still have to do is like have sort of examples on what other fields we would include in here. So like the sender and the recipient, which this example doesn't yet show. And in general, because of the change, we have to update the code, the implementation, and we also have to recompute the values. So the values that you see in here, the hexadecimals, they are not for the ciphertext and so on, is not correct, needs to be fixed. And we need to add some more examples, but that should be like uncontroversial. So I have the impression, and hopefully Lawrence too, and Ori, that we are getting closer to finalization. So cleanup and so on. But obviously, like we had lots of discussions and a long way to go with this. So, and as said, we still need to recompute the examples so they match actually. They are really verifiable and real example rather than fake ones. And include some of the parameters in the protected headers. So we accomplish the same what we had with the previous structure. But of course, you have to literally carry them in there, which is on a positive side, it's easier to debug for a developer because they literally see what is in the header field, and that's what they use to create as input to the HBKE invocation. Versus previously, you had to create this structure with values where if both sides got them somehow wrong because they got it from some other context which we didn't specify, so there's a potential to break things quite easily. So that's where we are. Any feedback on this?
Yeah, hi, I'm Sophie Schmeek, cryptographer at Google. You cannot actually protect the algorithm with the algorithm that is doing the protecting. That has to come from the public key. Like you have to have external confirmation of the algorithm. Otherwise, the algorithm, like as an attacker, I can change the algorithm to say none, which in COSE doesn't exist, but like assuming it does, I can change it to some algorithm that I can break.
Yeah.
And so if the public key doesn't tell me which algorithm is supposed to be used in this token, you're broken. So there's a security problem if you attempt to use the algorithm field in the token itself. You need to have the algorithm information must come from some other thing.
Can you go back a slide?
You can authenticate it, but the way that you authenticate it is by checking that it's the same as in the public key.
Mm-hmm.
Like so, like you can add it to the authenticated data. It just doesn't do anything.
Right. So what is the algorithm that we protect here in this? So this, let me. So the algorithm we are talking about here, this is the protected header field. It includes this algorithm. And anything that is in this protected header field. So in this example, it's just one. This is straight out of the document. So what we would include here, what would be something that is in the structure that we had in this HKDF context structure was the body U, body we identity. That's something we would have to include in here, but it's just not an example because, but those are the identifiers of the endpoints, and I believe that's important to include. It's not an example, but if we stick it in there, it would be included in the protection.
Yes, yeah.
That's
the identifier of the endpoints. Good thing to add in the associated data. The algorithm must come from the public key. Like you can put it in the associated data,
yeah.
sure, that doesn't hurt. It just doesn't authenticate anything.
Well, we have to put it in there because for other reasons, we can't just leave it out.
I mean, ideally, like I know that ship has sailed and crossed, gone around the world 5 times by now. But ideally, we wouldn't even have this algorithm here. Like this algorithm should be only in the public key ever.
Right. I fully agree with you.
The main thing that we need to point out in the RFC that nobody, like you must not rely on this header to determine anything, no matter whether it's in the associated data or anything. Yeah. The only thing that you do with this algorithm is to check that it's the same as you expected from the public key. Otherwise, you ignore it.
Yeah.
Humans look at it for everybody.
Yeah. Well, I argued with Jim back in the old days in COSE to not carry this stuff around, but I lost that argument. But yeah, it is what it is.
Ori?
Hi, Ori Steele. You're correct. So in HOSE and COSE, in public key representations, the algorithm is marked optional. So when we define new structures in HOSE and COSE, we encounter this over and over again. One of the main motivations for doing HOSE and COSE HPK together is so that key representations can have a consistent view of the algorithm that's used with HPKE. Even though that's an optional field, at least they can all, you could use a COSE key and you could do HOSE HPKE and the algorithm identifier would be the correct one, and the same thing in the other direction. So in public keys or private keys, when you're identifying the algorithm that key is supposed to be used, sometimes we use the term key restriction for that property. The purpose of registering the algorithms with IANA is so that when a public key contains an algorithm and that public key is only supposed to be used with this algorithm, that you can look up that algorithm in the IANA registry and you can identify, and make sure you trust everything that comes from the association to that algorithm. That algorithm is then also shown in the header here. So agree with everything you said. Thanks.
Okay.
Any other questions? All right, with that, Mike Prorock, let's talk about the post-quantum world.
Thank you, chairs, and in particular, Mike Jones, for letting me talk about the post-quantum world where everything is fuzzy, evidently. Now, we're going to talk primarily today about dilithium and Sphinx Plus, but there will be a note about Falcon here, right? Because that's definitely a topic. So next slide, please. So quick draft updates on dilithium. This is now, of course, way trimmed down from where we started because things are getting better defined elsewhere. And we can do things like point out to NIST documentation and say, hey, here's this, right? We've now got 204 to point at. And, did a little bit of cleanup, basically cleaned up, I think, all the IANA sections. This doc is in pretty good shape. So I think there's going to be an open question about probably an editorial pass, take any cleanups, and I would defer to the chairs as to when it's ready for working group last call. So that's, I think, where that one's at. And I am open to being wrong, but That's basically the status there. Mike, any?
The two standard questions. Who has read the recent draft? Not a lot. So who in the room or virtually in the room is willing to volunteer to read the draft? Michael, turn around. And so Roy, anyone else? Hannes, thank you. Who has implemented the draft? Mike has. Ori has. Did they interoperate?
Ori, have we done full testing on that yet? Probably will, but have not gotten there yet because things changed parameter-wise, so.
Okay.
Yep.
Ken Dang?
A question. I'm Quinn Dang at NIST. In these drafts, are we doing the poor signature, or are we doing the pre-hash version? We ought to have two different versions for those.
That's a great question. It's straight according to 204. We can add additional guidance, and this is one of the things that I think is a little bit open. Is if you go through and look at the LAMPS draft, right? They call out the notes around, hash first, then sign, etc. I think we're relying in this draft on the built-in like hashing internal, right? So, but there's options there. So I think that's why we need working group feedback. Read it. If you want additions there, please comment on the list so that we can incorporate.
Okay, thank you.
Ori?
So, Ori Steele. Yeah, so I don't think any of the tests that we have or any of the examples in the draft are pre-hash, and all of it's the IPD stuff. So, it can still all change, and part of the concern around moving these documents forward is like we want to make sure that everything's solid before we go forward. So as we get ready to start doing testing, we want to make sure that we're testing on the same parameter set. So I do think this is a case where it would be really awesome to have some tests and to use the implementation section in the document to refer to implementation. So if you'd like to work on an implementation of the IPD or the other versions, come talk to us, and we're happy to add your implementation to the references.
Can, as a subject matter expert, can you go to the mic for a minute? Yeah, I have a question for you. At what point do you believe we should have working group last call? Are there things we should be doing or not?
Since we haven't seen the final versions of both algorithms, poor signature and pre-hash signatures, so I think it's not a really recommended way to make a final call on a document which is not done yet. So I think we better to be patient and wait for the FIPS to be published.
Thank you. Okay, my sense as chair is we should get more reviews in. We should do the things that the reviews say. Interop testing would be great, and let's keep pressing on.
That totally works for me. I know we're somewhat waiting on this to come back with, when are we actually finalized, et cetera. So,
Yeah. Okay, thank you.
Great.
Thank you. Yeah.
Next slide. Similarly, and I did get some good IANA feedback just prior to IETF 120 kicking off. So there's some editorial and some updates there on the IANA sections that I'll be adding this week. I my personal sense from like a next steps here, following on the prior conversation, is let's just incorporate that. I would ask the chairs if we can get some folks to make sure we read, because I suspect the usual suspects around post-quantum are reading, but it'd be great to get some extra eyes, and it's closely related to dilithium. So if we could get some assistance there.
I'll ask the same question of the room in the virtual room. Who's willing to read this one? Roy again?
I know Hannes really wants to.
Do you want to read this one too, Hannes? The deer in the headlights look. Ken? Okay, thank you.
Excellent. And this is now aligned fully with 205 with references out to 205, which is an IPD. So once that moves out of IPD, then we can revisit the last call topic, maybe in Dublin. I don't know. We'll see. Next slide, please. Big questions for the COSE working group. Due to personal things, I kind of checked out of work a little bit for a good chunk of last year and kind of plugged back in this year. But during the course of that, kind of noticed that like, hey, there's not a lot of activity around Falcon, at least in my little world, right, that I live in. And that's my little world. Is anyone in the COSE working group planning on using Falcon? Or even if we aren't, do we think that that's going to happen? Very happy to do the work. Like, we got to go in, do a little bit of polish and things like that, but it's described working. But if no one's going to use it, I would defer to the chairs as to like, what should we do here? But I really kind of want to know from the group, like, is this planned for usage? There are definite use cases, particularly when smaller keys exist and things like that. So.
Roy?
Roy Williams. I was in a meeting in the hall where somebody from ARM was talking about using Falcon.
Raise the mic. We can't hear you.
I was in a meeting in a hall, and Falcon came up in the context of memory constrained device, so embedded devices. So they did voice a requirement for a viable Falcon implementation. Once again, it's hearsay.
Yeah, hearsay. That's kind of the hearsay I'm hearing as well, which is kind of like, yes, there's an embedded case. We need smaller keys, but I'll defer to the chairs. Like, I am happy to go through Revit, get it as polished as we can. I don't know if anyone has heard heads or tails from NIST plans on Falcon.
Good news. We are working on it, and we expect to have a draft sometimes later this year. That's what I hope. That's what we hope. We're working on it.
Excellent. That is great to hear. So with chair's discretion and feedback, what I will do is probably get the draft back alive with some editorial cleanup. And then as soon as we see an IPD or a draft out from NIST, we will rev it to align with that, similar to what we've done with dilithium and, well, MLDSA and SHS now. So
That makes perfect sense. Thanks all.
Awesome. I think that is it for my slides. I was trying to be efficient since we are a little bit packed. And I think defer to the chairs if there's any other next steps aside from that which we've covered.
No, we appreciate you doing the work.
Thank you so much, all.
Okay, with that, let's move on to CBOR encoded certs.
So, do I ask you to change slides or? So this is C509, and here are the updates. We have submitted 2 new versions. The good news is that we have gotten very much comments. The bad news then, of course, is that we are not as close to publication as we thought some while ago, but I think this is processing steadily towards publication, being more and more stable. some things we discussed in the past was that we updated the certificate types to not to avoid collision with some early implementations. There's been a lot of comments from Jun Liao, so bug fixes. Can go to next slide. So one of the main changes is that the signature algorithm, the position of the signature algorithm has been changed both in the certificate and the CSR structure. And this is to enable more efficient parsing of the structures. Then we have removed, added quite recently on the request, and then removed the special encoding for pen. After doing all the calculation, showed up that it saved some byte, but it didn't save very many bytes due to that you need to have a tag and so on. So it was not considered worth it due to the added complexity. In this self-signed certificates, we have a new value null to save space. That saves relatively much space. And then the certificate encoding. Next slide. So some more updates. And the first here, remove null option. That's only a change to the CDDL. It's not the change. This was not allowed before, but now we have updated the CDDL to be more strict. Then the null option is removed from key identifier. Next, and all the examples has been updated. Here's the updated CSR format, and there's some more details on challenge password formatting. So it's a lot of small changes here and there based on feedback. It's very good to have reviewers really reading the whole and implementing the draft. So next slide. And here are some pending issues about IP address blocks, certificate QC statements. Yeah. And then here there's been discussing how we should handle this mixture of CBOR encodings and their encoding. So to be able to support compression of current certificates without specifying everything, but also in a good way enable extensions in the future. And this we are continuing to discussing. Please review the drafts and look at these issues if you have any feedback. Next slide. Happy to report that we have new software that handles. For a long time, we have had software, reference software supporting X5092, C509. Now we have both ways, and we have an updated version of that software. It's support quite a lot in the specifications. With some shortcomings in the software. It doesn't support everything. We are discussing whether some things that are specified are not, we're not sure that it works. We would like to see example certificates for things. Otherwise, some things that we are not sure working might be removed, could then be added in a draft later if needed. We don't want to specify something that is then ending up not working. We would like to test things. Next slide. Yeah, that's it. We would like even more feedback, of course, on the changes, but I think this is moving along steadily, but it will be some more rounds before it's ready for publication. We still have open issues. Yeah.
Questions? Let's see, given the set of open issues, as chair, I would prefer that we find resolutions to the issues and some of the possible feedback from the chat before we do a working group last call. So I would ask the
Yes.
authors to let the chairs and the working group know when you believe all the issues have been addressed.
Yeah. We are, so far it has been coming new issues. We have been fixing a lot of old, but it's popping up some new. We will let you know when we think we are ready for working group last call. Yeah.
All right. Anything else for John? All right. Thank you, John. Next, we move on, I believe, to COSE receipts.
Hello, I'm Ori Steele. I'm here to present on the COSE receipts draft. As you can see, this draft was originally titled COSE Merkle Tree Proofs, and I think if you've been coming to IETFs, you've probably heard me stand up here and talk about this draft several times, so I'm hopeful maybe this will be one of the last times that I'll be here to chat. Next slide, please. So what are these receipts? You know, why do this work? So they enable COSE to express these proof types for verifiable data structures. What's a verifiable data structure? It's a term that we've used to generalize the transparency log infrastructure systems like what's used with certificate transparency. In that case, it's a binary, Merkle tree with the SHA-256 hash algorithm. But in general, a verifiable data structure is some data structure that allows you to sort of provide certain kinds of proofs. So proving that a given series of bytes are in a particular data structure is a useful building block for certificate transparency. It can be a useful building block for selective disclosure schemes. So in general, this document is describing how to put these data structures and proof types in the COSE and CBOR encoding. And as you can see here, the primary use cases are transparency logs in Merkle trees. The signed inclusion proof is typically what we call a receipt, and the receipt is sort of the most common proof type that we see floating around. But there's also signed consistency proofs, which are also called checkpoints in other systems. So you'll see this technology is sort of evolving since the original certificate transparency work, in particular in software supply chain scenarios. In the Golang ecosystem, for example, you'll see these things popping up. Next slide. So what do they look like? Here's some CBOR extended diagnostic notation. This is a typical COSE sign 1 structure, and you can see this unprotected header tag 394 includes some receipts, and those receipts are encoded. The rest of the structure is standard COSE sign 1. Next slide. So when we look inside of one of those receipts, you can see that this is a receipt that is also a COSE sign 1. I've got the protected header decoded here, and you can see this was signed with ES256, and that there's this tag 395 with a value of 1. And what this means is that we're using a verifiable data structure. That's what tag 395 says. And then the 1 is the RFC 9162 SHA-256 binary Merkle tree. RFC 9162 is the second generation document for certificate transparency, which I think the original one's like 6962. Don't get hung up on the topic of no one implements RFC 9162. It's the same SHA-256 binary Merkle tree. In the unprotected header, you can see this tag 396 with a map, and then tag -1 for inclusion proof. And this might be a bit confusing, like why have this map structure in the unprotected header like this? So as we looked at the different verifiable data structure possibilities, we wanted to plan for the future, and we thought that this map structure here could be a good way of handling some of the different possible encodings for proof types we might see in the unprotected header in the future. So the -1 is an inclusion proof, but that -1 is associated to the 3951 in the protected header for the SHA-256 binary Merkle tree. So for each verifiable data structure, you give that verifiable data structure an identifier like a 1 or 2 or 3, and then for each verifiable data structure, you count down, -1, -2, -3 for each of the proof types that that particular data structure could support. So the SHA-256 binary Merkle tree, it supports inclusion proofs, -1. It also supports consistency proofs. Those are -2. If we created a new verifiable data structure for the Merkle squared, transparency system that the key transparency folks are looking at, we would give that a different number, maybe like a 2 or a 3. And then we would have inclusion proofs, but we'd also have some of the prefix tree proof algorithms that you see with the other Merkle proof systems. The rest of the data structure here for the inclusion proof is the total size of the transparency log at that time. That's the number of leaves at the time at which the proof was created. The index of the particular object that we're providing a proof of inclusion for. And then the rest of the inclusion path, that's the path from the leaf to the Merkle root. And you can see the payload here is null. So that forces you as an implementer to recompute the payload in order to verify the signature. And that's a design, part of the design process for this particular system is to try and avoid a scenario where you might verify the signature and verify the inclusion proof, but not actually confirm that the root is the same for both. So we need to make sure that the signature that we're verifying is over the Merkle root, and we also want to check the Merkle proof. So if we check the Merkle proof first, compute the root, put it in the payload, and then check the signature, we can encourage folks to not accidentally forget to do that check. Next slide. So now we've got some CDDL structures. This is kind of just unpacking the EDN CBOR extended diagnostic notation you saw previously. These are very simple, so I think we'll just zip right through these. Next slide. Like I said, a receipt, that some of the language that we're using here is the receipts are signed inclusion proofs. It's the important part is, what extensions do we need to make to COSE to make these happen? So the verifiable data structure tag, which is just another algorithm identifier, but we want to make sure that's going in a protected header. And then in the unprotected header, these proofs. Why are the proofs in the unprotected header? That seems like scary, right? So the reason they're there is that these proofs, you're performing operations on them in order to get a value, and that the authentication process for them is a separate authentication process from the digital signature authentication process. So that's why they're in the unprotected header. It's also easy to add them later to something that was signed. So the unprotected header is a great place to put stuff, but you be careful what you put there. In these cases, you can always verify these verifiable proofs. So it's sort of okay to put them there, but again, with the unprotected header, be cautious. Next slide. This is just another look at the encoded version of a receipt. We've seen this in the earlier slides. We can skip ahead. So why do this work? Well, originally we needed a way to represent some of the transparency structures that the SCIT working group at IETF, Securing Supply Chain Integrity, Transparency and Trust working group, which is looking at software supply chain security scenarios. And we needed a COSE structure that we could use to represent these Merkle proofs. So That didn't seem like related to software supply chain. That seemed like a general security feature that everyone could benefit from. So that's why we brought this work to the COSE group. And the use case there was, maybe you would like to prove that a particular binary was in a transparency log. And that certain policies were applied at the time the binary was included in that transparency log. So I'll just sort of ad lib a bit up here about some of the work we did at the hackathon. So at the hackathon on Sunday, one of the things that I did was sort of look at incident response and how binary management can be a part of responding to a particular incident. So if you're going around to data centers, plugging in USB keys to recover devices, you might want to be assured that the USB-C contains authorized recovery material. Well, what does authorized recovery material mean? Well, one of the scenarios could be that you have a receipt that for this data center, this recovery material is authorized to be used in these computers. And what does that receipt convey? It means that before you let the recovery team into the building to plug in USB sticks, you're checking that the binary is in an append-only log. You have a signature on that receipt that's from a root of trust that that data center is associated with, and that the binary itself is signed by the incident response team. So that's an example of where might you want transparency when you're dealing with a particular security incident, and putting these things in a log is one of the things that we're seeing evolve in the supply chain ecosystem. Next slide. So where are we at? We're at 05 now. We've requested early allocations, and I've been speaking to the chairs about the process for that. And the reason we're asking for these early allocations in IANA is those tags 394 and 395. We like those numbers. We want to be able to do implementations on top of them, and we think maybe we shouldn't have to change them at this point. So let's ask for early allocations. There's some interoperability work that's already been done here. I think there's at least 2 implementations of these receipt structures at this point. Although I will say, part of the agility around the verifiable data structure piece is that people like to make different log formats. The SHA-256 binary Merkle tree is a pretty good log format. And I think it would be great if there was more interoperability implementations around just that SHA-256 binary Merkle tree. That's the implementation that's compatible with Trillion, but there are other Merkle tree systems out there that that produce different roots. And if for the same binary, same set of messages, you get a different root, that's the sort of signal that you're going to get a different verifiable data structure. So when we talk about interoperability in this space, we need to make sure we're talking about we both support the same digital signature algorithms, but also that we both support the same verifiable data structures in order to get these inclusion proofs. There's been some feedback from Robin, gave a great review of the document on the list. Authors need to respond to that review and complete and address all of those comments. And I should mention, I have
What's Robin's last name?
Bryce, I think. Yeah. So he gave a wonderful review of the document. I should have said at the beginning, this is work with co-authors Hank and Cedric and Antoine, who I don't know. Hey, I don't think they're here, but they've been helping along with these documents as well, and so I'm hopeful that they'll respond to Robin's comments. I think that's it. Oh, this is the most important part. We're really struggling to get reviews, and this document I think is really ready for working group last call. We've got a couple implementations. So respectfully to the chairs, I would like to ask for a working group last call on this, but I'm happy to answer any questions from the room or from folks who are remote. Thank you.
All right, I'll ask my standard questions. Who has read the document? Mike Prorock has read the document.
John Geeter.
John has read the document.
We have a Q remote.
Okay. Okay. Felix, go ahead.
Hey, just a question about the remark you made regarding unprotected headers. It makes total sense what you said, but then I was wondering, what are the purposes of the signature in that case anyways?
Yeah,
Like,
it's a great
it
question.
makes sense for a signed tree head because by definition that is signed, but yeah, why do you want to sign?
Could you go back to any of the diagrams that have one more? This one's good. So here we've got the inclusion proof structure and the unprotected header, and this is the structure of the receipt. So the receipt itself is a signed tree head. And the authentication material for the Merkle proof side of that is in the unprotected here because you're going to use that information to recompute the root, and then you're going to verify the signature. Can you go back one more?
So it's basically in the signed receipt is 2 and 1.
Signed, yes, it's
Yeah.
two pieces of authentication material and one conceptual message. Yeah,
Okay,
that's
that
correct.
makes sense.
But the other point here is there's another unprotected header, and you see there's multiple receipts. So imagine I've got a really high value binary that I'm using in an incident response scenario, and I want that binary to be transparent on multiple transparency services, maybe independent agencies, different regulatory environments, whatever. So one of the nice things about the unprotected header is it's mutable without breaking the signature. So we can add those other receipts over time for this recovery material. So I might mint the recovery material, go to a vendor and say, hey, I've got the recovery material. You want, can I fix all your devices? That vendor says, yes, but make sure it's transparent in our transparency log system that we support for our data centers. So I would register the recovery material with their system. I would come back with a receipt for the recovery material, fix all their boxes, go to the next guy. It's a different data center, different infrastructure. I say, hey, I want to recover your devices. He says, yeah, but we have a different transparency system. So I could get a receipt for that same binary, but in a different system. And that's why you see multiple receipts here. And you can see them in the unprotected header because we want to add them over time.
Yeah. And here the protected header is again a signed tree head,
So
but only for one of the receipts.
yeah, so this is the what we call in Skit, we would call this a transparent statement. The payload is detached here. Think about filling that payload with some important binary in the incident response toolbox, or an image that you're trying to secure, or some other artifact that you want transparency on. So here, the payload is some application or domain specific binary that you're trying to secure, whereas inside of the receipts, the payload is the signed tree head.
Okay, cool. Thanks.
Yep.
My other standard question is who's implemented it? 3, that's good.
3.5.
Good. Have you tested with each other?
So this is back to the point about the SHA-256 binary Merkle tree. That's the implementation that I've been using to test. And I have done cross testings with the Trillion open source implementation to make sure that the Go ecosystem's Merkle trees are consistent with the implementation that I've done.
What open issues remain for the draft?
I believe at this time, the primary open issues are the ones in the follow-up steps to review and respond to Robin Bryce's comments, which he sent to the list some time ago, and which I'd love for our co-authors to respond to. I can do it, but I would love for other folks to work together on this. And then the early allocations piece as well. This is more of a process thing, not something to change in the document.
Okay, similarly to the previous set of presentations, why don't you tell me when you think you've addressed Robin's comments, and then we'll start working group last call.
All right, so let the record reflect that we're not ready for working group last call until Robin's comments have been addressed. Thank you.
Thank you. timestamp tokens.
Yeah, hello. I'm here for Henk, who is chairing OPS AWG at the same time, so he couldn't be here. But this is probably one of the more obvious drafts that I have talked about. So Ori's slot was a pretty good preparation for this, because this is again about something that looks a bit like a counter signature that is put into the unprotected header, but also sometimes in the protected header. I get to that. And this time it's RFC 3161 timestamp tokens. So this is a little bit of a blast from the past. These things were standardized like 20 years ago. But there is infrastructure out there that provides them. And so if you just want to use this infrastructure to say, I have some data structure here, and this guy over there vouches for the data structure having existed at that particular point in time, then timestamp tokens are a good way to get existing implementations and existing services. So that's why we are doing a little bit of some mixing here. So I think the idea about saying next slide is that the slides advance when I say next slide. So the previous slide said that this is just to be used for signatures, COSE sign and COSE sign 1. And we have two modes. And the slide you see is the first of the two modes, the timestamp then COSE mode. So in this case, actually the timestamp is part of the information, or becomes part of the information that somebody wanted to sign. So that's why the payload is both put into the SIG structure from COSE and into the TSA, the timestamping agent mechanism. And the timestamp token that comes out from the TSA is then put into the SIG structure and signed. And in this case, obviously, the timestamp goes into the protected header, because the originator of that COSE structure wanted to make sure the timestamp is with the data and the timestamp cannot not be meddled with. And next slide. The other way of using the timestamp token is to do sign 1, and maybe independently of that, maybe even at a later time, actually ask the TSA to timestamp that signed structure. So that timestamp then, of course, only can go into the unprotected header, just like the receipts we had before. But the semantics here is not that of a receipt, but of a timestamping token. So this is all pretty much no-brainer. And I can imagine not many people have read this because it's so boring. Next slide, please. There was some recent comment on how we should deal with the fact that there might be some information leaking. And we added some text or the authors added some text to the security consideration section. I think that's the one thing that needed to be done. And the authors think this idea is ready for working class core. And I should say it's actively being used in the Reds context, so it's a good thing if we do this reasonably quickly.
Thank you, Karsten. Emergency presenter. Are there questions for Karsten? Mike Rock.
Sorry, trying to meander to the mic here. Mike Barak, I was going to note, in addition to rats, we're doing some testing already with using this parameter in other contexts of signing evidence in external use cases. So definite uses elsewhere. And likewise, I think it's ready for working group last call. It's able to be implemented cleanly.
Thank you. Indeed, it's a very, very general box that you can add to your kit and do a lot of things with.
Are there implementations?
I cannot answer that.
Mike raises his hand. All right, this does a simple thing. Hearing no objections, let the minutes record that we're going to start a working group last call on this draft.
Thank you.
Thank you, Karsten. It is time for COSE hash envelopes, which Steve is going to talk about.
Hello, I'm Steve Lasker. See if we can get a non-animated deck here. So this was something that Ori, myself, and Hank have been working on. It came as part of Skit, but it turns out this pattern's fairly generally used. So we wanted to bring this forward. So next. So first, just kind of a reference point for what the current state is. So next slide. So basically we've got the protected header, which has a content type in it that is what the payload is. Great. So then we put that payload and then the content type of the payload and then other parameters in there, other headers. And then you have the payload itself. And that's fine when you're trying to pass something around. Next. And then you sign those bytes, but the signature is based on the payload and the protected header. You need that combination. Next. So when you're trying to submit this COSE object up to various services, such as a Skit transparency service, how does size matter, right? How big is this payload that we're trying to send over? And is it referencing something that already exists? So in the software case, everything that we're talking about putting in the payload is already in a storage service of some sort. Why are we flooding the internet, sending it around? Again, is it the same thing? And is there any real benefit? So in the normal case, or not the normal case, but if you just take the protected header and the unprotected header, sorry, the protected header and the signature, it's 2K, big deal, right? Maybe for the CBOR group as a whole, where conciseness was key, that's already too big. Next. But if you take any reasonable SBOM or vcon or container or some of the packages, they get awfully big. And I don't think we want to be passing these things around. So that's kind of the impetus to starting this. Next. So then we have detached payloads. Sounds like a great solution. Well, detached payloads just say they're detached and empty. So if you try to check the signature, you need the payload. So all it did was allow for out-of-band delivery of very large payloads, which we already have another service. Now we could use the unprotected header or protect, doesn't really matter, to tell us where the payload is. And if it's accessible, we can go get it. Next. And then you'd be able to verify the signature. The signature would pass because you'd be able to compare those, the payload and the protected header. But that's a big if. Next. Because in many of these cases, those storage services may not be accessible, or we're just back to the same size matters. There's a lot of content to be passing back and forth when all you're trying to do is check the validity of the signature. Is the issuer somebody you want to test, get content from? I refer to this as the Trojan horse scenario. I don't want to bring the binary onto the machine to check if I want the binary. I want to, right? Because it's too late, right? This is kind of like you go to passport control, you hand them your passport. only if they like you will they let you through. They don't let you through first and go, aha, I've got you, and then validate whether you should be there or not. Yeah. So give you your passport back was Mike's comment. Next. So now, all right, so let's start thinking about some other parts to it. Well, what exactly are we putting in the payload, just to kind of add to this? And this was meant to be a build slide. You could have A equals B, fairly simple, inline content, no big deal. So size doesn't matter in that case. It could be a small file, well, define small, or it could be a large file and define large, right? These things have varied over time and per industry. Could be a collection of files. Might be a files by reference, such as an NPM package URL or a container image package URL. In fact, in those cases, those are actually manifests, which are yet more files that contain links to files. So what exactly is this payload? Next, please. Turtles all the way down. So now this is where we start evaluating the hash envelope, please. And that's kind of the point here is there's a lot of complexity. Like, which one are we trying to choose? When we were rolling out Skit and data trails, we were trying to communicate to partners like, well, when should you use this API and how should you use it? And it was already like they're trying to get something else done, and now it depends. So as you go through this, inline, the colors kind of indicate where that's good and bad with this little legend at the bottom. Detach didn't really solve anything because you still have to provide it. It's just out of band. So what if we use a hash payload? Next, please. So in the hash payload, we're taking the payload and hashing whatever the original contents was. So now you actually have something to verify. So you don't need to bring down the 50 terabytes of that large language model. You can say, here's the hash of it, and you need to make sure the hash matches, but at least you have a verifiable signature. Now, this has been a little bit of the accuracy is true problem in that we'd like to have used the content type that was already there, but the content type is a hash. So we had to introduce another type that says, here's the pre-image content type. So now you know when you're undoing that hash, what was I trying to get it to? And the SPDX example is an interesting one because they come in JSON, they come in YAML, they're XML, maybe even INI, I forget. So you know what the original payload was supposed to be, the content type. Now the payload location is interesting because it's really kind of, I don't want to say it's optional, but it's like that's, if you want to, you can go get it. That may not be where you get it. Best practices for any software is don't go out to the internet to try to get something you already are dependent on. Take possession of it and deploy it locally. So your copy is still the same hash, even though location is someplace different. So the hash is really important in those cases. So what's nice about this is, one, they're independently verifiable. Size does not matter in this case because you have a nice compact hash. And we're not trying to recreate the data that's already in these storage services. Next. So an example, so in this case, the algorithm, we're leveraging the new type RFC 9596, where, and we can debate, I think we already had some feedback, is that the right IANA type? And we can certainly take that as a change. You know what the algorithm was used to hash, so you don't have to guess. We'll expose what that is. What was it originally? And then where is it stored? But again, the where is it stored is not hardened because you're probably, that might be where it was signed in the first place, but as you're referencing it, like such as I already have a copy of it, you can use the hash. As long as the hash matches, the location is not really as important. Next. So we've already got a couple examples of how we use this. This actually was one of those that came out of necessity. So we're referencing it in some GitHub actions we use for Skit. It turns out that DigiCert was already doing this with their software trust manager, where they're hashing their content which them of many people do this, so it's not a new thing. And vcons also can be very large in size, so they're also very interested in using this. So that's, I believe, what I have next. Yeah, so this is an ask for adoption. So please review and any feedback, and that's the info. Justin.
Hi, Justin Richard. So the obvious issue with any detached hash space mechanism, right, that is that you still have to calculate and validate the hash. Otherwise, you just kind of blindly accept everything. We see this all the time in HTTP message signatures that use content digest and things like that. I've seen a number of implementations in the wild that naively check the signature and then walk away without checking the content hash. Is there anything we can do beyond sternly wording warnings in this draft that would make people, that would make people not skip the hash check? I know some data structures have inherent means of doing that. I don't see that here. What are your thoughts on this?
I mean, Roy's up next. I mean, okay, I mean, I would just say that it's obviously none of this stuff solves laziness and that kind of stuff. There's best practices to make it efficient. Does not mean you're still going to skip security altogether. Nobody confirms that you have to go check any signature before you deploy a payload unless you have something in place. So that same logic, I would say, should be in place.
Could I?
Wait.
Just.
Oh, sorry.
I do think that this particular issue is a little bit more subtle than that, because you can put in work to check the signature and convince yourself that you've actually done the right thing. That's where I see this particular problem in the wild. It's not, oh, I'm just going to skip security, because that's kind of a bigger, dumber decision.
Fair enough.
So, go ahead.
Lawrence?
I was going to answer this
Okay.
question. So Roy Williams. So in the situation where we're using this as a method to notarize or countersign, yes, this makes perfect sense for here, but the end user that gets this still has to validate the content, because they're going to get the content. And you're right, we should probably put wording that's where this gets stitched together, and I have no problem with that. In the mode where this is, it saves network bandwidth, and we're not attesting to the content in some of these cases. We're attesting to the signature, which is slightly different. But yeah, I agree with your statement.
Okay. Yeah, thanks. That it is helpful in the more ways that we can have that kind of stitch the pieces together in here that are lightweight for implementers. I think we'll be better off that way. Thanks.
Lawrence.
That question. Yeah. Okay, Michael here. So okay.
It's moving up the queue.
What I was hearing in the question, and I'm asking question or clarification, what I was hearing was maybe it would be good to have a hash over the first 100K, okay, such that when you go to fetch the 6 terabyte file that doesn't fit on your disk at all, that you can start off and get a little bit and go, yeah, this is going the right direction. And so it's worth my 6 hours to download the rest of it to get the thing, as opposed to, well, that's just not the right URL. Okay, let's stop right earlier. That's what I was hearing in the question. I don't know if that's a good idea, but that's what I was hearing in the question of the process, right?
No, it's interesting to say that, okay, to Roy's point, part of it is this content from somebody I trust? But that's the main thing that we're kind of trying to address, is because multiple entities can sign some content. And in fact, what we define in SCID is multiple entities may agree or disagree whether they believe something meets some behavior. And so you check the one you trust. You ask the person that actually knows about how to build a house, advice, as opposed to somebody else that doesn't. So I think there's a first check there, but I think you're at that next part of, from a validity of the integrity of the content, does it match? That'd be the interesting optimization. Lawrence.
Yes, so this is close to, this solution is close to the solution for another problem that with COSE assigning that I've run into. That is when you want to assign something big multiple times with multiple algorithms and you only want to hash it once.
Yep.
So it just seems like, because you can encrypt multiple times with COSE, but you can't sign multiple times with COSE and hash once. So I don't know if there's a way to combine them, but just.
That's a great point. Mike.
Yeah, Mike Burrock here, big +1 to Lawrence, definitely a common pattern we see. One option that might be worth considering is kind of forcing a strict mode, and I think this goes to Justin's comment where potentially the hash itself is what's in the detached payload and getting signed.
Yes.
So it's just not present at all. You have to calculate the hash in order to verify the signature, right? So if you leave the hash out of, that's being signed out, right? There might be a way to force that somehow, right? Creatively. So. Might
No,
not
that's
be
a
suitable
good
for
point.
all cases, but there are cases where, like, if you need this absolute, you want to guarantee that the person receiving this does compute the hash and verify, right? There are cases where that's critical.
No, that's a good point. You could, in that case, it's attached hash payload, I guess, if you will. But that's a different, I would argue that's a different scenario, though, because in many of these scenarios, I don't want to download, it's the Trojan horse thing we just discussed. If I download it to get that hash, then I've lost already. So it depends on what you're trying to verify. Ori.
All right, or Steele. Michael Richardson reminded me that COSE sign 0 exists. So most of the time when we're looking at these, we're talking about COSE sign 1, but maybe sign 0 with this structure sort of solves the case that Lawrence, you were talking about. I don't know. Do people use COSE sign 0? Doesn't it? Doesn't? Sorry, man.
So definitely people use COSE sign 0. I'm a little out of date. I haven't been paying attention to this for the last year or so. But I know a couple years ago, I did look into trying to deal with multiple signatures, particularly for a hybrid PQ scenario, right? And hash once and verify. And my recollection then is COSE sign 0 did not help with this. That there was definitely something needed. And I think if you go back in the mailing list about 2 or 3 years, there's I think I posted something.
Do I have to download the whole mailing list or get a hash? Sorry.
Just the first 100 messages.
The first couple of K, yes. Anything else?
All right, we're going to use advanced Medeco features now. All of you who haven't joined via the Lite client, this is your opportunity to do so. Get your name on record and express an opinion about whether it's appropriate to adopt this by the working group. All right, going once. Who's still trying to join?
Well, now we'll know where his vote goes. He's been identified.
Okay, let the record show that the room and the virtual room were in favor of adoption. So I will follow up on list or my co-chair, but it looks like we're going to have a new working group draft. Thank you very much.
Thank you. I don't know if I mentioned, because I left, did I mention Ori, myself, and Hank are the authors of the draft? I think I left that off.
Okay, and let the minutes let the minutes record the 22, 0, and 8, if possible.
Recorded.
22-0 and 9 now. With that, we're now going to start on a festival of Hannes presenting 3 times in a row. The first one
Sorry that you guys have to go through this.
that Hannes has volunteered to talk about is the following.
Yeah, it's a pretty long and complex title, but you will see the familiarity very quickly as I go to the next slide. So this is so there's this. If you have attended the last year November IETF meeting, the LAMP session, you've seen a talk with AAD to non-AAD downgrading attack to CMS. And it's an attack where an adversary manipulates the content encryption algorithm identifier from, for example, AES GCM and downgrades it to AES CBC, for example, or counter mode. And thereby, if it is successful, so there are a couple of preconditions, and there's the link to the LAMPS draft below. But if the attacker is successful, then he's able to impact confidentiality and the integrity of the payload. And it's not a totally unrealistic attack. And that's why there is a document in the LAMPS working group to mitigate that attack, which has, as I noted here, has gone through working group last call in LAMPS already. So it's a kind of mature solution. The solution is somewhat simple. Namely, what it does is it's normally you have the key distribution algorithm. For example, you use something like ephemeral static Diffie-Hellman, and then you derive a content encryption key. And now what that document in LAMPS is indicating, you go through another key derivation step and you include the this encryption algorithm identifier as well to make sure that you come up with a different key. So if an adversary is able to modify or modifies that algorithm, he would then end up having a different key, and then consequently the attack gets discovered. So this document, after looking at the COSE work, which we believe this attack is equally applicable to, we propose a mechanism that follows the same line of thinking and applies it to COSE. Of course, considering the different payloads and parameters and so on we have in COSE compared to CMS. And yeah, so that's in a nutshell what the document does. It's quite short. But it's obviously important to address that vulnerability or that sort of attack before it becomes an issue. I've been working with Ken Takayama and Russ Housley on this document, but the document, this specific version of the draft, the 0.0 version, was submitted in a somewhat of a rush before the deadline, so I didn't have their permission to include them as authors. And yeah, that's why they are not there yet. So that's something I need to do. Another step is to look at how this attack could eventually be applied also to COSE, which I would then say we should, in the same style, also apply the same mechanism to COSE. So this is, when you remember my previous talk and a comment from Sophie earlier, that this is the different algorithm. So this is like, if you remember the picture with the diagram, which had these 2 layers. We were previously talking about the recipient layer. That was the HPKE discussion. This is sort of the outer layer, the content encryption layer. So it concerns this one. So there's essentially then an extra layer of key derivation that is taking place, which in my opinion is a minimum amount of overhead, but there's obviously benefits to be gained from that. So that's, for that reason, I'm asking for document adoption of this one and to process the document as quickly through the working group as possible to avoid having problems in the future.
Any questions?
The alternative would be to also have that algorithm in the public key itself. So if you don't want to do the key derivation, you can also say this public key can only ever be used with this envelope, with this data encryption key type. Mostly a question of whether you can afford an HKDF or not.
Yes, good point. So I should have mentioned that. So in the HBKE case, since we are right now working on it, we could include that mechanism, and in some sense we did, but there are also all sorts of other key distribution mechanisms in COSE, which we don't want to change again. Like, we don't want to update the whole COSE thing. We want to basically take what we have and add that on top of it. And so the question is, of course, like, as we work on right now on the COSE HBKE, should we have then a linkage to this document, or should we incorporate the technique into HBKE and have this sort of apply to the rest of it? But yeah, I think that goes into the direction that you are asking as well. And I don't have an answer to this right now. I think this is something we need to discuss on a mailing list.
Mike Unsworth. You are muted. Let's go on to Lawrence.
You're
until
still
he-
muted, Mike.
Lawrence?
Yes. So Ken Takayama produced some very pretty diagrams that he posted to the mailing list that show a couple of the solutions to the attack that was presented in Prague. My understanding from that is that this is one solution, and this is the solution that CMS chose. There is an alternative solution, which is to feed the identifier of the algorithm of the next layer down into the key derivation, or or more correctly, into the authenticated data of the COSE recipient. This is what Hannes presented in his warm up to the festival. And so I think we have to pick one solution or the other. I mean, and to me, I prefer inputting the algorithm ID. I think it is a much simpler solution and much lighter touch. This adds a whole other layer of processing. And just when I think about the amount of implementation work and object code, this seems more complicated.
I'm not sure. I wouldn't agree with you there. So that the HBKE solution is obviously something. It's easy for us to make changes there because we are already touching on many other things. We are designing the mechanism right now. But if in order for this approach to work for all the other sort of key distribution mechanism, we have to then touch all of them. Like, we have to look at all of them and figure this out on how exactly this works. And that could be tricky. Like, there is AES key wrap as a mechanism. There is sort of ephemeral static Diffie-Hellman. You have static Diffie-Hellman. You have all these sort of things, and we then have to work through all of them. That sounds like a lot of work to me. And so for that reason, I prefer to be in line with what the CMS or /LAMS guys came up with. Even if we decide for the HBKE case or for future mechanisms to have something else.
Yeah, agreed that we need to look at all of them and understand that. And I don't think that has been thought through completely yet.
Yeah. Well, it's we just, like, I think 2 weeks ago I submitted the document, so it's.
Ori.
Hi, Ori Steele. I like the solution because it's simple and it aligns with how LAMPS solved this issue. I queued to come up to basically say the public key restriction comment that you're making. We talked about this a lot with COSE and HOSE HPKE, and cutting straight to the chase, In COSE and HOSE, there's never been a way to restrict a public key to a content encryption algorithm, as far as I'm aware, ever. Right?
Well, this specific attack, so I think we have to distinguish between the outermost layer, which is the content encryption part, which this attack deals with. This is sort of the AES GCM downgrade to AES CBC. The other aspect, which we discussed earlier, is what happens if someone modifies the algorithm in the recipient layer, which of course is also a problem.
Which they're going to do because
yeah.
they control it. But to coming back to the point that we spent many hours discussing this on these lists, and it just keeps coming up over and over again. The algorithm identifiers in the keys are optional, and none of the algorithm identifiers that are going in the public keys are restricting to a content encryption algorithm. You're inviting this thing forever, right?
Yeah. Yeah, I think the reason why we have been discussing this topic up and down is simply because it's a little bit convoluted to understand. It's not so easy, or for some of us at least, and it's the attack side. It's not like, oh, if you omit this, then here's the attack. You actually, the attacks, and you have to construct them, think about them. Since we come up with building blocks, some of those, omitting some of those context information structures, for example, like the endpoints that we discussed earlier, it's not that the attacks are immediately obvious. And so that's why maybe it makes it more complicated.
So just one more comment. There's this draft fully specified algorithms. I'm an author. Mike Jones is an author. It's been presented in the HOSE working group yesterday. And this topic of algorithm constructions for hybrid encryption, and with that, when I say hybrid, I mean hybrid public key and symmetric encryption in this context. We've tried to write text around this topic in that draft, and if we acknowledge the trend that we've been on, that text would basically reinforce this pattern of never restricting an algorithm in a public key to a content encryption algorithm. So if you're passionate about this, I encourage you to also read that draft fully specified algorithms. I'll put it in the chat. If you want to see text in that says something about restricting a public key to a particular content encryption algorithm, that draft could be a good place to put that text. Negotiating that in that draft could kill that draft. I mean, we could talk about it forever, but we should. That's a place where we could put that guidance. This document, I'm not sure that I would mix them together at this layer, because this is just about actually using the parameter that you're seeing in the header, right? So you're not talking about public keys here. You're talking about safely using parameters in an attacker controlled message.
Yeah. So I took one interesting point that was discussed yesterday at the HOSE meeting with me, which is the bullet number 3 here. Use algorithm identifier to signal this mechanism, because somehow we have to indicate of like, oh, you're doing this additional step of key derivation. You need to tell the recipient that you actually do this. And so I include the parameter in here, but I actually like the suggestion that was made yesterday in Mike's presentation better, which used a different algorithm number. Since we are changing the algorithm numbers, or presumably, depending on how that discussion goes, we could actually sort of indicate that, well, if you use, for example, ephemeral static Diffie-Hellman, then there's this new algorithm number, and it actually means that you do the traditional ephemeral static Diffie-Hellman plus this key derivation step, and then you're good. I hope that made sense. But
Mike Unsworth for the second time.
Okay.
Let me try my audio this time. Better?
Works.
Works. Okay. So my question is technical. You've probably said it and I probably missed it, but what are the backwards compatibility implications of doing this? Does it require new code points, new algorithm IDs?
Yeah, new algorithm IDs in this case, yeah. Yeah. In my opinion, like
for which?
Yeah. So, yeah, that's a tricky thing.
New for the AEADs, or new algorithm IDs for the public keys, or for the fully specified? Like, how are you fixing this?
Okay.
What layer are you?
So there are a few to be done here. So I think what I'm asking is like at this point in time is, since this is like a very recent submission, is like recognition from the group that this is a problem we need to address, and there's a problem statement, and we have some prior work from the LAMS working group on CMS, and to start work on this and not acknowledging there are some questions. I think that's I don't have the answers to your questions.
Sophie?
Yeah, it needs to be in the public key that you change it. You can't do it in the AED. The AED cannot attest to its own algorithm. The other thing is, if you have a new algorithm identifier, you could restrict the algorithm of the data encryption layer if this is a direction you want to move to. Like, it is okay to have more than one data encryption algorithm. I consider it usually bad form to have more than one data encryption algorithm associated with one public key. So if it was according to my personal wishes, I would restrict it in the public key already to just one data encryption algorithm. You're not introducing any vulnerabilities if you do the derivation, but if you're already changing the algorithm identifier for the public key, you might take that as an opportunity to fix the public key to one data encryption algorithm if that is something.
Okay, so when you say sort of tied to the public key, you mean like you envision something like a COSE key structure which has all the parameters, and then there's one additional flag that says I used it with this one. Okay.
If you look at the HPKE, that already does that. The HPKE already says,
sure,
I'm using this curve and also AES GCM. If you do that for all of your public key types, you've also mitigated it, and you don't need any HKDF things. That being said, putting everything into HKDF is always a good idea, so do that as well.
In HPKE, actually, so that's a tricky one, because in HPKE, it actually has two meanings. So there's one case, that's the single layer, the integrated encryption, direct encryption, where the AES GCM usage really applies to the plain text you are encrypting. So there it works, but in the other case, in the two-layer structure, you actually have the AES GCM potentially twice. Once you apply it at the recipient layer to the KEK, and then another layer, potentially you use a different algorithm there, you apply it to the actual plain text. So
in that case, I would even call that algorithm HPKE P256 AES GCM AES GCM.
Okay, and that's not what we do today.
Yeah, I understand it's not what we do today. I'm just saying that is another alternative that I think has some merit to be explored.
Okay, that's another thing then to take into account, which unfortunately also says that like there's open issues.
Lawrence, then the queue is cut, and then I'll ask a question.
Yeah, so just real quick, this all kind of gets intertwined with the COSE layering. You know, COSE layering, there's a COSE recipient and there's a COSE encrypt, and you can layer them, usually just two, but you could even do more. And I think this solution kind of hops around the layers. Anyways, we need to think about the layering, COSE layering, and the modularity of the layering in whatever we do here.
Fair enough. Yeah. So I think we can't go directly to working group last call yet.
And we've burned through our 10 minutes spare time at this point, but who is willing to read this draft and post a review on list? Ori, Lawrence, Sophie, Kang? Yeah.
I quit.
Okay. Okay. Thank you. With that, we
need to speed up.
We continue with the festival.
So I speed up a little bit to make up for the. No, this is wrong. This is the.
Oh, sorry. How about this one?
That's cool. PQ key. Is that?
And you have 10 minutes each for the two remaining drafts.
No, I'm not. I'm not going to talk about this one
You're not going to talk about it.
because I spoke about this one. Maybe a mistake in uploading. I spoke about this one at the COSE meeting yesterday. Yes, that's the one. So, how many of you have been in the COSE meeting yesterday? Raise your hand. Okay, actually a lot of. So I can skip a couple of slides. Next slide. So I talked about like all this transition path. I talked about like all the work that great work that NIST is doing. Yesterday I focused on the far end at this part where I was talking about how to encode chems in specifically COSE and also COSE. Now I'm actually talking about the one in the middle to deal with a hybrid scheme, namely a hybrid scheme that once was as a cipher suite defined in HBKE, which added hybrid as the combination of traditional, next slide, the traditional and the post-quantum crypto. Here's a reference to this definition from the BQ draft. And we had this in an earlier version in the HBKE because there was work done in the CFRG to register cipher suites for HBKE to support that functionality, the hybrid functionality. We stripped it out again in a later version of HBKE because we said, oh, this will take much longer. First of all, it takes longer for NIST to get their act together, and then it takes even longer for the CFRG to complete that work. And so we do it later, and that's why now, I think now 1 year later or so, we now have put that, specifically this feature with the corresponding text into a new document. And this is this document. So there's related work, or conceptually at least, work in DLS and in IQ version 2, where hybrid designs are specified, but those hybrid designs are not using HBKE, but this is HBKE focused. Next slide. I should also point out that when you use the combination of the traditional and the BQC algorithms, you somehow need to combine these two shared secrets that get derived. And there's this combiner work, and there is the solution that we are using is currently specified in this CFRG document that is referenced in the draft and also later in the slide deck. But there's a more generic solution that was just recently proposed called X-Wing by Deirdre, which may be used as well in the future. So there's some ongoing debate about this topic as well. Next slide. Also, limitation worth pointing out for this specific work. HBKE has different modes. There's an unauthenticated mode called base mode, and then there are 3 authenticated modes. And this specific hybrid combination only works for the base mode, so for the unauthenticated mode, which means that you additionally have to use other COSE constructs outside the COSE payload to provide that type of authentication. For example, you could use the COSE sign 1 along with it. Okay, next one. And so this is the algorithm registry that this document proposes. So this is in the middle. You can see that this is this hybrid sort of algorithm identifier or algorithm label that is being used, this X25519 Kyber construction that was proposed, and this is basically what the document suggests to be added along with the text explaining what it means. Okay, next one. I think that's so. Yeah, so it's still sort of work in progress in terms of working the CFRG and also NIST and so on. But it might be a good time to nevertheless think about adoption and to get some experiments being worked on to see how well that works and who is then interested in these hybrid modes. Yeah. That's the short version.
Questions?
What do you think? You care about hybrids? Sophie does, yeah. Not everyone is excited about hybrids. Some people think we should go straight to post-quantum crypto, but so your mileage may vary here. But yeah, I think like as a big fan of HPKE, I find the solution using a hybrid with HPKE good. So.
All right, Ori Steele, can you go back to the algorithm identifier for a second?
Sure.
So the just because you put it up here, I think both HOSE and COSE have moved on from putting the HPKE mode in the algorithm identifier. So you have HPKE base here, but you could have had PSK or basically just PSK because hybrids don't support any auth mode. So just saying that out loud, because if we do an HPKE hybrid in COSE, it's sort of like, of course we'll do one in HOSE, right? We would want to be able to restrict a key to the specific algorithm. We would need to align around all of that. And then the other comment is it says Kyber, but should say ML Chem, and it should be the not IPD version and all the other stuff we said, right?
Yeah, so that's what we copied from the original specification, the CFRG specification. So that's why it looks like this. And I agree, yeah, they should update that as well. And the work is still ongoing. So it's I saw that Westerban and Wood refreshed the document. So it's alive and kicking. So we'll channel that feedback to them. And then Mike.
Any more questions? All right. Like the last draft, my sense is this is pretty new, right?
Well, it's compared to the last draft, this was actually in the COSE HPKE draft as a registry, but without the text in an earlier, a year ago or so. So we just sort of took it out and took it in this draft. But so in that sense, it's not totally new versus the previous version that was like the attack that was published was from November. So it is fresh.
Okay, who is willing to review this draft? Or at first, who has reviewed this draft?
I just did. That's
It's short.
Come to the microphone. Or
Quinn said it's short. He just did.
Oh, okay.
You didn't pay attention to my presentation, just read the document instead. Okay.
So Quinn, can you write something to the list?
Now you basically raised your hand, Quinn, and now you need to review.
I'm Quinn Dang. I think it's a good proposal and I support adoption.
I'm first looking for how many people have actually read the draft before we ask the adoption question. Okay,
It's really a code point allocation. Well,
Sorry, Ori Steele. So maybe a better question is, who's gonna deploy this code point if it gets registered? Like this whole hybrid, pure PQ or hybrid debate. Like it's easy to get code points, but who's gonna use this thing? Come to the mic. Tell us you're really excited. You're only gonna do concise embedded IoT in hybrid because you care about conciseness. That would be my question.
Yeah. And I fear the answer is probably not so easy because many companies haven't made up their mind on those issues yet. Except maybe Mike has. Oh, you want to go straight PQ? Yeah. Okay. Yeah. But it's a.
I know that we will use it if we use COSE for something PQC. I'm not sure if we're using COSE for anything in that realm right now. Probably yes, but I'm not sure how much we're using the encrypted COSE. That is the only caveat. Otherwise, we will definitely use hybrid PQC.
Yeah. Okay. So maybe this is a sort of a call out to the community. I will obviously ask people, and specifically you, like sort of maybe you haven't asked inside your companies among your colleagues on like what story you want to go for in sort of moving to post-quantum, whether you wait and can go for PQ directly, or maybe you go through an intermediate transition path. At least the work in DLS and iQuestion 2 gave me some confidence that some people want to go along the hybrid path. In general, like the whole PQC topic is difficult for constrained IoT devices. I think that's not news to anyone here. So that may be a challenge all along. But yeah. Anyway, said enough. I'm out of it.
Ivo, I'll say something, then you speak up if you like. I think I would like to ask Ori's question on list, which is, if we do this work, are people wanting to deploy it? I think the work is well defined. Question is applicability. Ivo, do you agree with that course of action?
Yes, that sounds fair to me.
Okay, so Justin.
Justin Richard, just as a general technical point and not necessarily specific to this, you need to keep in mind induced demand for something like this. Some implementers won't touch it until a code point exists. And it might be what somebody will or actually use, and it's very, very, very hard to predict that, especially in a space like this where there are lots of different algorithms and methods and ways to go about doing this. Very clearly, as we've heard from the room, some groups are very much not interested in doing this. So I think it might be harder to make that judgment call of, is this worth doing because, you know, our people want to do it? Because are there people who want to do it because they might not be able to say that they want to do it until it's a thing that they can do?
Okay, with that, unless I'm wrong, I believe we are through our agenda. Are there things people would like to say at the microphone? And if so, please join the queue before we call it a meeting. All right, thank you all for good discussions, and thank you, Michael, for taking
It was all Christian.
the minutes. Thank you, Christian. The minutes are going to be very important to the chairs for us to be able to determine what to do next. Thank you all.
Thank you.
Yes.